It's gonna go live, but it's gonna be a different URL. So I'm gonna have to give me a minute to tweet and write it on the old.
I'm happy to write in chat, in the YouTube chat.
Thank you. I'll tweet that and then I'll get it started. So, okay, this is the URL. I send the link on the Zoom chat. Okay. All right. I think maybe we can get a start. Let me start the recording. Oh, okay, great. Thank you very much, and sorry for this delay. We will have to debug what happens with the live stream. But thanks Fatemeh for taking the time to prepare and give this talk. We're really excited to host you here virtually, unfortunately. So Fatemeh is going to talk about overhead techniques for privacy and fairness of deep neural networks training and inference, like you can see from the slide. She's a PhD student at UC San Diego. She's been working a lot on trustworthy machine learning and NLP. She's got a bunch of awards, like the National Center for Women in IT Collegiate Award in 2020 for her work on privacy-preserving inference. Got a Qualcomm Innovation Fellowship in 2021. She was a finalist. She's done internships at MSR, and overall, she's done a lot of work on what she's going to talk about today. So without further ado, thanks, Fatemeh. Take it away. Thanks.
Thank you so much for the introduction, and thank you everyone for coming. I'm really happy to be here. So I'll start the talk. Okay, I'm going to start by just emphasizing the importance of privacy in our everyday lives. We have all, wherever we are, we're at home, we're at work, or we're going to the hospital, there's always all these devices that are collecting our information. We're being watched, we're being listened to, not by necessarily a malicious party, but there's all of our information that is being gathered through sensors, cameras, smart home devices. So what happens is that this information is collected and it's sent to cloud service providers that we might trust or we might not trust them. Even if we do trust them, they might be compromised at some point. And it's sent to them, they're processed. There could be like a machine learning algorithm that is running, and we get a response back from them. So you call, you say, hey, Google, and what's the weather going to be like tomorrow? It collects your voice. Maybe if people are talking, in the background, it also collects that. It sends them to their servers, and then it gives you back a response. Now, what makes this setup really sensitive in terms of privacy is that you could be sending your voice, it could be footage from your home, your patient history, or your genetic data. So it's very sensitive in terms of privacy, and in nature, it's not something that you would want compromised. So if we want to have a high-level look at mechanisms and different methods for preserving privacy, really high level. If we look at their privacy utility trade-offs, so one group of methods are methods that rely on noise, adding noise, or just applying noise through different mechanisms, like differential privacy, or local differential privacy, where you're adding noise to the data, or training when you're adding it to gradients. Different mechanisms for adding noise. What happens is that you're just adding this noise without considering the accuracy or the model or assuming anything about the utility loss in order to get any meaningful privacy. So normally you end up with models or with data that has very little signal left that you can work with in order to get privacy guarantees. Another group of methods are encryption-based methods that give you, they give you security. You have rigorous guarantees. You also normally harm your utility, not much, just a few percentages maybe. But the problem is that right now, the methods that we have that do use encryption, like homomorphic encryption, secure multi-party computation, they are much slower and they're much more compute intensive and also communication intensive compared to conventional training and inference. So it might not be a suitable approach for like real-time setups or edge devices that are resource constrained. So they might not be applicable everywhere. So that is the whole encryption-based methods. Now, what we're trying to do and what a lot of researchers are trying to do is to kind of push this curve for the accuracy agnostic noise addition up so that you can get closer to getting better, more meaningful privacy without having to sacrifice a lot of utility. And in this talk, I will discuss some of our work, which tries to approach this ideal state for both inference and training. And I'll start with our ASPLUS 2020 paper named Shredder, which focuses on inference. Okay, so the execution model for Shredder that we have introduced in the paper is where you have this pre-trained model, a neural network, that a service provider could be using to give you a service. Like you send it images, it tells you if someone is smiling or not. And what we do is we partition or split this network into two segments, into two partitions. The first one is less compute intensive. You can run it on your device, and the more compute intensive parts are offloaded to the cloud. In the edge partition, what we do is we run the few layers of the network, and when we get the intermediate activations, we don't just send those, we add some noise to them, and this noise is sampled from a distribution that we have trained before. So how do we train this noise distribution, and what is it exactly supposed to do? So this noise that we're adding to our intermediate representations, what is special about it is that you're trying to engineer it in such a way that it's tolerated by the neural network. So whatever the main network is supposed to do, if it's supposed to detect the smiles or guess a number or something, it does that correctly. But we try to reduce other excessive information that might be within the intermediate representation. So we're trying to remove whatever is extra and just send as much signal as needed. And how we do this, how we get this noise and how we find it is through a gradient-based method that I'll explain. So normally when you're training a network, what you do is you find the gradients, you use backprop, you update your weights. Here, what we're doing is we're adding noise to an intermediate layer. So what we do is we freeze the rest of the network. So all the parameters, we assume they're frozen and we can't change them because normally if someone else is deploying a model, they're probably not going to change it because of you. So we assume that it's frozen and we're just trying to find this noise. What we do is similar to how backprop normally works, but this time we're doing it for a noise tensor. So we have this tensor which is initialized randomly, and we are now trying to only train its parameters, change them, such that we find this tensor that we like that is, the network is resilient to. And we do this by doing backprop, but not changing the weights, only doing backprop until we reach this noise tensor and, updating this noise tensor. And what is good about this method is that, you can use any objective function as long as you can differentiate it. And it's also non-intrusive to the model. So if someone doesn't want to cooperate with you in terms of changing their models, but they're giving you their parameters or their architecture, then you can use this. And you can learn this additive noise patterns for every layer. So which layer gives you the best execution time and communication, you can choose that layer to apply this method. Okay, I'm going to now explain how we actually train this noise and how we actually use it. So what we do is, we take a pre-trained neural network, we split it, we take a noise tensor that has the same dimensions as our intermediate activations, we initialize it with random noise with high standard deviation. So it normally harms the utility of the model at first. We feed, we sample a batch of data, we feed it through the first few layers of the model, we get intermediate activations, we add this noise tensor to them to get noisy activations, we feed this to the rest of the model that is supposed to be on the cloud, and we get the output of the network. Now, at this point, once we have the outputs, there are two possibilities. One is that you test these, you get their accuracy, and they haven't reached a desired level of accuracy yet. So if this happens, what you do is you take another batch of data, train, update the noise tensor again until you do converge to a desired accuracy level. And once you have reached that level, once you check your accuracy, okay, this is like good. And now this means that like this noise tensor, this pattern is kind of a pattern that is tolerated by the model. So what we do here is that we fit a Laplace distribution to this tensor. So we take the mean and standard deviation, we find it, and then we see if it's a good fit. So if this noise tensor actually fits well to a Laplace distribution, and if it does, we collect the parameters, the 2 parameters of the distribution. And we also collect the order of the elements. So we're not saving the actual tensor and reusing it, but we're saving its order. So like which element is the biggest one, which is the second biggest, and so on. So we collect the parameters, we collect this ordered distribution from this tensor. And then during inference, once we have deployed our model, what we do is we just sample from this distribution, and we populate this noise tensor, and we add it to our intermediate activations and send it to the cloud. So this is the overall how this noise pattern training works. And the loss function that we use is relatively straightforward. It has 2 terms, a cross entropy term that is there to preserve the privacy of your model. You don't want to add too much noise. And at the same time, you also have a privacy term, which tries to increase the magnitude of the noise. It's kind of implicitly trying to increase the standard deviation so that you're like removing more information. That is why it's there. It increases the magnitude, and also we have a parameter alpha, which is like a knob trying to tune privacy and utility trade-off. So if you want like more privacy, you want to sacrifice more utility, you can increase this alpha here. In our setups, normally like in the in shaders, like default setup, we assume that you only have this main task that you want to do, and you want to add as much noise as you can. But you could have more directed setups where you say that, okay, I want to like do this task well, but at the same time, I want to protect a certain attribute for which I have labels. Like I want to protect people's age, I want to protect their genders, and I have the labels for this as well. So if that is the case, we can also add an extra term, an extra cross entropy loss, which is there to minimize the accuracy for that particular task that you're trying to protect. So it's kind of the negative of the cross entropy loss that helps the utility. So you can also add this to have a more directed type of noise addition that tries to protect a certain attribute. So this might be a good place to pause if you guys have any questions from the noise training and the patterns that I explained. So if there's anything, I'll take it now. Okay, I'm gonna move on then. So moving on to the experimental setups, what we did was that for our edge devices, we used Jetson TX2 boards, and for our clouds, we used the Titan XP GPU, and we also used PyTorch for both the edge partition and cloud partition to execute the models. We also used a bunch of data sets, MNIST, CIFAR, SVHN, ImageNet, VGG, and 20 newsgroups, which is text corpus, and it's used for classification of news, for topic modeling. And we have a lot of experiments in the paper. So if you're like interested in how we chose which point to cut the network, because that is also another problem. You wanna get good execution time, and at the same time you don't want to have a lot of communication. So there are some studies on where to cut the network that it's like most efficient. Which layer to add noise, how does it differ where you add the noise, what kind of privacy utility trade-offs you get, and also like comparison to previous work. So you can find all of those in the paper. And in the interest of time, I'm only going to show you two of the main results. So one is the main, accuracy privacy trade-off graphs that you see here. So here the y-axis is the privacy that we've used mutual information in terms of bits. So it's the information between the raw image and the intermediate activation that we're sending. And the more information that is lost, it's better. And the zero leakage is actually like the ground amount of information that is in the queries in the data that we're sending. So if we reach zero leakage, that means perfect privacy. We're not sending any information. At the same time, it would probably mean zero utility as well, because you're not sending anything. So you can see that, as you would expect, the higher the better privacy you get, the more loss in accuracy you're going to endure. And if you want to choose like one point to use for deploying your models, it'd probably be the knee of the curve where you're getting close to the zero leakage line, but still the plot hasn't plateaued. So you haven't hit diminishing returns yet. So that would be a good cutting point. And another interesting result that I wanted to show is execution time. So intuitively, one might think that, okay, if I'm not executing everything on the cloud and if I'm offloading some of it to the edge device, then I'm going to have worse execution. Whereas that's actually not the case. We're in fact getting a speed up on average when we're using this splitting scheme. And the reason is that if you look closely here, you can see that the dark, like navy blue bars, they represent communication. And for the cloud only setup, that is what actually takes up most of the time. So the problem is the communication, and the main problem is that we're sending the raw data itself, which is huge. And if you have a resource constrained device that is not good with sending huge data loads, then you're going to have a long execution time. Whereas when you're sending intermediate activations, they're like smaller in size normally, and therefore it's easier to send them. It takes less time. So overall, you end up having a faster like end-to-end execution. So to just summarize, Shredder, Shredder gives you faster execution. It gives you enhanced privacy on average. I'm really like careful with those words because you're using mutual information, and that is an average case notion. So we're not giving any worst case guarantees, but on average, it's better. It's better than nothing. It's also not giving you any overheads. So, it's better to use it, but there are some issues too. So one issue is that this was really heuristic based, right? You learn this pattern and then, you fit a distribution to it. Maybe, maybe it fits well, maybe it doesn't. Then you have to choose another pattern, and you're also using the order of elements. So it's like not very, clean. And also it doesn't really give you much insight, right? Like if you look at the noise tensors that you're adding, it doesn't tell you what features the model is actually using, what is important, what is not. So in the next work that I'm going to talk about, we tried to address these issues. So this was a 2021 paper. So any questions from Shredder? If there are any questions, I can take them now. Okay, cool. Okay, so in Cloak, what you're trying to achieve, it's the setup is kind of similar. It's still inference. And you're still sending a query. Is this person smiling? There is still this like deployed model, and you're getting a response back. And the threat might be someone who's intercepting your connection, trying to get the data that you're sending, or they are they're compromising the cloud and trying to access your data there. So the main difference here with Shredder is that we don't assume like any splitting. You're just this is like a strongest setup where you're just working on the actual data input itself, and we're trying to figure out what features the model is using to make its decision and only send those. So it's in a sense more principled. And also another good thing is that here you don't need any collaboration from the service provider. So you don't need to have their parameters. We show that even in a black box setup, you can use this method. So even if they don't want to like give you their architecture or do anything to help with privacy, you can still take some control and apply this without their help. So how does Cloak actually work? Like, what is the intuition behind it? The intuition is really simple. So we say that if you have an image, if you take part of it out, like here you take the lips out and you query the model with, is this person smiling? Odds are that the response you're going to get is is a low accuracy response. The model is not going to be able to make a decision. So this means that the feature that you removed was important. Now, if you remove part of the head, which is not so important, then what you end up with the query of, is this person smiling? You're going to get good accuracy even if you remove this. So this shows that, this is a feature that is not that relevant to the task that you're running. So if you're using this intuition that if a feature is important, then, removing it is going to cause loss in accuracy. And what you're doing is trying to find features based on this. So we take an image, we call each pixel of it a feature, and we create, again, noise tensors, but here we have the actual parameters of the noise. So we're training the standard deviation and the mean of the noise directly instead of trying to infer them and fit distributions. We're directly trying to train standard deviation of the noise. And once the training is we take samples and we get the noise tensor, but once the training is over, looking at this standard deviation tensor can give us an importance mapping. Right, if a pixel has high standard deviation, then it's probably less important. But if it has low standard deviation, then it's more important. So this is the overall intuition behind it, looking at standard deviations for each pixel that the model can tolerate. And all these distributions for each pixel, they're all independent. So we're sampling them independently from each other. It's not this large, a large distribution which has many parameters. It's not a multidimensional distribution. It's multiple one-dimensional independent distributions. And we sample this noise, we add it to the image, we get the noisy image, and we send it to the deployed model. And and this is like an image of our suppressed representations. You can see that the person's lips are visible because that's what the model was using to make decisions for smile detection, but the rest of the features are jumbled because they were irrelevant. So this was the main idea. Now the loss function, it looks kind of complicated, but it's still very simple. You have the cross entropy term that is there to make sure that the noisy representations that you're generating, they still have high accuracy. And also you have a privacy term that is there to make sure that you're increasing the standard deviation of the noise. So the difference here is that there we were looking at the magnitude of the noise and implicitly trying to increase the standard deviation, but here we're directly optimizing the standard deviation. And we again have that trade-off parameter. There are some issues here that you can't really backpropagate into a distribution. You can't just sample from a distribution and then update its parameters. So we had to do some reparameterizations there. And also if you update standard deviation with backprop, you might get negative standard deviation. So we also had to address that. And in order to address that, we had to do some more reparameterizations. You can find these in the paper. But the main point is that we show that if you use this loss function, you are decreasing the upper bound on the mutual information between the image and the unrelated irrelevant features that are inside the image. Okay, so that was the training. You use that loss function. Again, the model is frozen. You're only updating these the noise parameters. And once the training is done, you have reached the desired level of noise that you want to add. What happens is that you get this noise tensor, and by looking at it, you can be like, okay, these pixels are important, these pixels are not important. But the question now becomes, how am I going to suppress features that are less important? I figured out that, okay, these features are not important. How am I going to suppress them? So one way is that you can just threshold the standard deviations and say that, okay, if for a pixel, a standard deviation is higher than a certain value, what I'm going to do is I'm just going to say that this pixel is not important and I'm going to remove it. So how do we remove it? Again, one way is to just replace that pixel with 0. And what happens if you do that is that we've observed, and you can also see it in the graph here, this green dotted line. If you just replace pixels with zeros, it's like you're turning the image entirely black. And if you're suppressing a lot of pixels, so if you're only wanting to send some features that are important, if you suppress all the features, what ends up is that you're going to lose, you're going to lose all accuracy. And the reason we hypothesize is that the model is like not used to seeing all black images. So it's kind of out of domain for it, and it can't really give you an educated guess on what the image was. So you're going to lose utility if you replace with all zeros. Another thing you can do is that you've been training with the noise, right? You were sampling and adding noise, so you can also just sample from this high standard deviation noise and just add it to the model. Add it to your image and send that noisy image for inference. That also works. So this is like this blue line here, and it also works. But the best thing you can do, which is like what we're proposing to do, is to suppress with constant trained values. So you can, instead of like 0, you can also train the constant values that you want to suppress to. So this will be a second round of training where it only takes a couple iterations. You just find what pixels the model is used to seeing, what kind of colors, and you just suppress the pixels that you want to suppress with those, static constant values, and you replace with those. And we observe that this is best both in terms of accuracy and also in terms of privacy when we try to mount attacks, because you're actually like replacing with static features. It's hard for the adversary to reverse engineer those numbers. So are there any questions from how Cloak works and how we train it?
I believe there's one question from the chat from Hide. Apologies if I missed. So it says, thank you for the nice talk. Why are you using noise here? I believe it referred a few slides before. Why are you using noise here and not just masking individual pixels and that is setting them to 0? That's the question.
Yeah, so that's a good question. The reason, so it's, I can give 2 answers. So the first one was that because what we wanted to do was to easily train. We actually tried just like blocking whatever number has a high standard deviation, just blocking it even during training. So not sampling from the noise. And that ended up being bad in terms of convergence. It didn't really work well. So the noise kind of did a smoothing thing that was easier to train. And also another reason behind it was that if you look at the paper, because of the information theoretical bounds that we're trying to enforce, using Gaussian noise, it's like easier to get the math to work out. So there's another reason. And one final reason is that in terms of finding the gradients, with the reparameterization trick with the noise, it's really easy to backprop into standard deviation and mu. But if you want to just replace things with 0 pixels, it kind of turns more into an RL problem. I think it's like you zero out the pixels, you feed it to the model, you get a response back, and then from that feedback you change things. So I'm not sure if it would be easy to implement. I mean, in terms of gradient, finding the gradients, you would probably have to use RL in that case, because you're just removing the pixels and it's no longer continuous. So that's actually 3 answers, but yeah, those were the answers I had. I remember we tried something without still with the noise, but we didn't send the noisy images. We would just map whatever noise we had into static suppressions, but the model wouldn't converge in that case. So this was with the noise, the model actually converged as well. And something nice that in general, with both Shredder and Cloak, when I was running the experiments, I observed is that adding noise really helps generalization. So I did sometimes even with a small noise end up with better accuracies than I had from the pre-trained model, slightly better, but still. So it helps with the test accuracy. Yeah, I hope this answers the question.
I suppose so.
Okay.
Oh, yeah, they confirm. Yeah.
Great. Thanks. Thank you. Okay. Great. So now I'll show some qualitative results of what happens when you apply Cloak. So Here we have 3 tasks, hair color detection, glasses detection, and smile detection. And what you're seeing is the mask of, high importance feature that we decide to keep based on the feedback that we got from the model. And you can see that it's very similar to what we humans use. So for the hair, it's like the top of the person's head. For glasses, it's the eyes. And for smile, it's the lips. So it kind of makes sense. And if you want to push this further, because, you can change that lambda parameter, and you can push the noise further to get more privacy and suppress more features. So then you would end up with fewer features, as you can see in the second row, and you're also losing I think around 10 to 15% accuracy in the second row. And what the actual cloaked image that you're sending looks like, it looks like this last row. So you can see the person's hair and their eyes and their lips, but the rest of it, it's completely suppressed and jumbled. And again, this is like constant values. So this is what the neural network was expecting to see, which is also interesting, the colors and how it looks. Yeah, so these are the representations that we get, and this is what we're sending to the cloud. And so in the next result, here we're looking at the some quantitative results. Here we've mounted an attack on Cloak. So the setup is that you have Cloak representations for smile detection. So smile is supposed to be shown. You're supposed to have suppressed the rest of the features, and you're seeing the accuracy for this main task in the y-axis. The x-axis shows the accuracy of an attacker who is trying to infer other attributes other than smile. So it could be hair color and eyeglasses. And for each of these, attackers, we have assumed 2 access levels. So the blue and green one are more limited access where they can only query a limited number of times. So they can't, they can only see get representations for limited images, and then use those cloaked representations to pass them through their trained models and infer hair color or eyeglasses. But the orange and red lines, they show a stronger setup, a stronger adversary, which can query the model infinite times. They can query the model as many times as they want. So what they do is they feed their entire training set to Cloak, get cloaked representations, and retrain their models in order to maybe reconstruct or kind of reverse engineer Cloak and figure out the hair and again eyeglasses attributes for the images. We can see that in the less stringent setup, it's very easy, like with losing around 5% accuracy, less than 5%, you can get this adversary to be random. So you sacrifice very little accuracy, and you can get a random adversary that can basically infer nothing. But in the setup where they can retrain, it's a bit harder. They can probably infer information when they train with their models. So maybe they're getting biased somehow, or maybe there are some features for some images that leak, and they can find, like when you're looking at the smile, maybe for some people, their eyes are lower so they can see the glasses. And when they're training, they're retraining their model, they gain better accuracy. But still, if you sacrifice a little more utility, even in this setup, you can still get near random behavior from the adversary. So it's harder if the adversary has infinite query access, but still you can get some good levels of protection. Another thing that we studied here was the fairness. So our intuition was that if you're removing a lot of features, then maybe if the model was biased towards a certain gender, like in a certain decision, maybe this bias is also removed or mitigated. So what we did was we looked at 2 fairness metrics: demographic parity, the green one, and equalized opportunity, the red one. And sorry, it's actually the orange one, it's this one, and demographic parity, the blue one. And basically what is important here is that the x-axis shows fairness, and the lower this fairness metric is, you have a better fairness, you have a more fair classifier. And also the y-axis shows the accuracy. So the main task here is hair color detection, and we've chosen this because this is normally more biased by gender. So it's like mostly like in the data set, we observed that mostly females had blonde hair, so the classifier would be biased. But we also observed that when we're removing excessive features and we're only like sharing this top of the head and we have removed the person's face, then the bias is actually mitigated. So this can also help with that. Of course, if whatever was biasing the model was important in terms of the classification, like if it was glasses detection and you can see the person's face, then this wouldn't work out this way. But if the features, the biasing features and the important features don't overlap, then we are observing some improved fairness as well. So with this, I'm going to conclude Cloak. So we saw that like we have interpretable privacy. You can actually see what you're removing, what's happening, what the model is looking at, and you can also get fairness in special cases. But the problem it's that with the constant suppression values, and also when you're training the standard deviations, you end up with a constant map for each model. Like these are the features that this model is looking at on average. But maybe like there are samples that they aren't exactly like that. So you're not getting dynamic features for each sample. And this has a relatively easy fix, right? If instead of training the standard deviations directly, you use an autoencoder that also looks at the input of the image and then generates standard deviations, then you can fix this and get dynamic maps, which is what we did in a short follow-up paper. It was just an application. So here, I'm only like going to go over it shortly. But what we did was we applied Cloak in a medical setup for pancreas segmentation. And what makes pancreas segmentation difficult is that the pancreas, which is the red organ, it moves around in different scans based on the angle. And it also moves, it looks different with its size, again, because of the angle. So it could be anywhere. So one thing that like the researchers are looking into is how do image segmentation models find the pancreas and what they rely on. And what we did was we used Cloak to actually interpret. So this is like more of an interpretability issue to interpret what the model is looking at. And if you see in these animations, as you're increasing the noise, apart from the pancreas, there is the kidney and some other surrounding organs that are the last ones to be removed, which means that the model is actually using kidney and some other easier to find organs to anchor itself and then find the pancreas. So that's also like a nice observation that you can see that the kidneys are the last to go. Yeah, so that was it. If you're interested in like applications, you can check out this paper. Yeah, so are there any questions on these 2.5 papers that I discussed so far? Okay, great. So now I'll shift gears a little bit and talk about our work on preserving privacy of training data for text generation models. And this was the work that I did with at my internship at Microsoft Research last summer. Okay, I'll start by just talking about language models a little bit and providing some context. So language models, neural language models, are these relatively large models that are trained in an unsupervised manner on huge corpuses of data. So it could be, normally this data is scraped from the web. So there's very little observation and provenance on where it's coming from and how it's scrubbed. It could be company websites, news, data sets, emails, social media, whatever is available. And these are used to train a large recurrent model or a transformer model in order to guess the next word. So you feed the model part of a sentence, and then you train it to give you the best possible guess for what the next word is. So the main goal is to learn the structure of data through guessing the next word. And in a recent paper that actually Nicholas Carlini presented, I think it was 2 seminars ago here, and he talked extensively about it. What they showed was that they used OpenAI's GPT-2 model, and they found that if you give it the certain prompt you see on the left, you can actually extract a real person's physical address, phone number, corporation name, and and their email address. So, and they also checked this with OpenAI, and apparently this person was like really in the data set. So although this data is, public and, it's supposed to not have any sensitive issues with like privacy, but still we see that there are information that can slip through the cracks. And, if it's happening with OpenAI's GPT-2, it could definitely happen with other models. So the main problem is that there are two problems. One is that you're normally dealing with data that can have sensitive information. And two, it's that you're using these high capacity language models that are also known as the statistical parrots. Sorry, I think it's stochastic. I don't remember what the title of the paper is, but there's this recent famous paper. But basically, they're like parrots. So whatever you feed them, they repeat it. So they're memorizing information. They could be generating private data or even unethical data. So there are a lot of issues surrounding them. But the problem that I want to focus on here, it's the memorization. How can we train these models so that they memorize less sensitive information and are still good in terms of the utility that they provide? So one, easy, not easy actually, but the first thing that comes to mind is to use differential privacy. So how would we use differential privacy in this setup? In the most relevant paper, it was used with federated learning. And how it works is that on each device, you have your data, you train models on devices, and then before sending their gradients, you clip them, you send their gradients to the cloud, they're aggregated, noise is added to them, and a central model is updated and sent back to the devices. So the most important point which relates to differential privacy is that you clip the gradients for each user's data, and then you add noise and you aggregate them. So why don't we want to use differential privacy, and why are we looking into alternatives? So the foremost issue with differential privacy is that it's actually a good thing, right? You get worst case guarantees, no matter what your data distribution is. You are protecting every single token in your data set, every single person, every single contributor. And that is good, but it's bad because not every single token necessarily needs protection. So by doing this, you're also harming the model's utility. So normally these worst case guarantees come at a huge cost to model utility. And this is more prevalent in larger models that have huger space of parameters. You're adding noise to every single parameter, which causes really bad utility. The second thing, which also relates to the first one, is that you cannot explicitly define protected attributes. So maybe you just want to protect someone's age or their political views. And you don't need to protect their every single utterance. You don't get that with differential privacy. You don't get to choose what you want to protect. So again, you end up sacrificing a lot. A more recent issue is with disparate impact. So differential privacy has been shown to be worse, to cause more loss in utility for underrepresented groups. So if you have minorities in your data set, they are the ones who are going to see more loss in utility. So the poor get poorer. If they already have low representation, they're going to suffer much more from this differentially private trained model. And another issue is that if you're dealing with larger models, that even without differential privacy, they take a long time to train. This is going to be much worse when you use differential privacy, because for DP you have to clip gradients sample-wise, so you can no longer parallelize a batch, and you have to find gradients for each sample in the batch, separately clip them, and then aggregate them, which causes 10 to 15 times a slowdown compared to conventional training. And this not only is like harder to train, it's also harder to tune parameters, because you can't train multiple models and pick the best privacy utility trade-off. So training is very costly using differential privacy. With all of those issues in mind, we were thinking of proposing a method that can optimize for a certain notion of privacy or a certain attribute that we want to protect, and at the same time, in a regularizer-based manner, optimize for the utility as well. So here we define privacy or privacy breach as, if you have a string and you can use this to link this to an author. So just by seeing the string, you can guess who the author is. Then there is probably a privacy breach. And if someone can extract this sentence, then there's a privacy breach. If this happens, then when you're training your model, you should probably change the encoding of the model of the sentence so that it can no longer be linked back to the author. And you can do this for any attribute. Again, age, political views, gender, anything that you want to protect. So the first regularization that we introduce, it's an adversarial learning one. So what we do is we take a sample, we feed it to the language model, we take a training sample, we feed it to the language model, and just with the output of the language model, we can calculate the cross entropy loss, which is like the loss for predicting the next word, and use that for utility. For the privacy, what we do is we take the embedding, the encoding of the model for this sentence, which is its last last hidden layer representation. We extract it, we feed it to a discriminator, which is a simple, I think 2 or 3 layered classifier that we use, and we ask it to guess who the author of this sentence was. So it gives a probability distribution over all possible sets of authors. Like here, it's saying that, okay, probably Alex has written this sentence. And then we use this output distribution for 2 loss terms. One of them is for the loss of the discriminator itself. It's a cross entropy loss. We want the discriminator to be as good as it can be, because the better the discriminator is, the better insight we get into what we need to change. And at the same time, we also want the language model to generate representations that are harder to link back to authors. So we're decreasing the KL divergence between the output of the discriminator and the output distribution of the discriminator and the uniform distribution, because we want the discriminator to become random, right? We don't want it to just have bad accuracy, we actually want it to be random. So we are using this KL term to make the output of the discriminator closer to random. So to recap the training for this adversarial loss, we have 2 separate loss functions. One for the language model, which optimizes the language model's parameters, and one for the discriminator. For the language model, similar to before, we have 2 sets of terms: utility term, privacy term. We have a trade-off. We have a lambda, which allows a trade-off. But for the discriminator, we have only 1 loss, which is its cross entropy loss, to protect, to preserve its accuracy. We also introduced the second regularizer, which we call it the triplet-based regularizer, or also declustering. And how it works is that we remove this discriminator. We no longer use a discriminator. What we do is we take another sample of the data at the same time, and we feed it to the model again, and we get another hidden state representation. Now, with these 2 representations, we generate our privacy loss, which is it's very simple. It's the L2 distance between these 2 representations. And if these 2 samples were from the same person, you want to increase the L2 distance, because you don't want data from the same person to get clustered in the encoding space. Because if that happens, then it's easier to extract it. But if it's if it's all over the place, if it's a spread around, then it's harder to reverse engineer and find the author. So what we do is we're saying that if the samples were from the same people, try to increase their L2 distance. But if they're from different people, actually try to get them closer to, fool any adversary who is trying to extract information. So again, we have 2 terms, but here we don't have a discriminator. We only have the language model, you have the utility term and the privacy term. Okay, so for our results, in the paper you can find an exposure metric, which I think Nicholas also talked about, training time, an tau attack that we mounted, and the impact on different subgroups. But again, for the interest of time, I'm only going to talk about the last 2 here. So if you're interested in the other 2 results, you can look at the paper. Okay, so what is a tab attack? The tab attack is kind of just a simple attack that we mounted to see how well the models are doing. And it's very simple. You prompt the model with like saying, I will, and then you press tab and tab and tab again, so that the model gives you an output. So here it's like leaking, I will meet Alice at the docks. So this way, if the sentence that the model produces was actually in the training data, then we consider this a success. And we use the accuracy of this tab attack as a metric. So here you can see this attack mounted for the 2 data sets of avocado and Reddit. So avocado is an email data set. It's a smaller, Reddit is a larger data set. And for each of these, you see 2 bars, synthesized and real canaries. So synthesized canaries are sentences that we have randomly generated. They're not necessarily grammatical. We have just put them to have a control hold on the data. And real canaries are some random strings that we have selected from the training data. And we have tried to extract these from the model, and you can see the accuracy of this attack for those samples. And the main, what is important here is that for our regularizers, the triplet and adversarial, we see that the attack is less successful. This is more apparent for the synthesized canaries in avocado case. And the reason that it's more apparent there is that avocado is a smaller data set, so memorization happens more. And differential privacy is adding noise, so it can only protect so much. And if you have a sentence, or if you have a sensitive query like your employee ID, something that only you talk about a lot, differential privacy is not good at protecting it. But because our methods are actually, if you have repetitions, they're actually better at figuring out who it relates to. They are better at protecting you. So the summary is that, if you have some sensitive information that is repeating in the data, then these types of regularizers are better at removing it than differential privacy is. And one last result that I want to show is the fairness, the impact on different subgroups that I talked about. And here the two bars kind of show well-represented and underrepresented groups in the data. And the main takeaway is that the gap between these two bars is really high for differential privacy, but it's much smaller for us, which again goes to show that differential privacy is having a worse effect on the underrepresented groups. It's dropping their utility more. Whereas our models are not really that sensitive to different subgroups, and there's this small gap between how the model works for different groups. Okay, so I'm going to conclude the talk here. We talked about some different privacy preserving mechanisms. We saw how they affect fairness, how they can be better, or with differential privacy, how they might be worse, and how this privacy utility fairness might interplay. But there's still a lot of things that need to be explored, like how can we even get privacy and fairness, like rigorous privacy, like differential privacy and fairness at the same time? What is causing differential privacy to be unfair? And how can we get maybe rigorous guarantees for all of them together? And this was just a centralized setup. So what if we have a setup like federated learning, distributed learning? How do all of these interplay together there? There's not a lot of work on these things in federated learning setups yet. So how does that work out? And all of these, again, for natural language processing, there's very little work on privacy, and there's more work on fairness, but little work on privacy. So there's definitely a lot of different aspects of these problems that still need to be explored. So with that, I'm going to conclude the talk, and thank you everyone for listening. And if there are any questions, I'd love to take them right now, or you can also reach me by email or any other means. Thanks.
Hey, thank you very much, Fatemeh. Really great talk. Great. I see a question in the chats of the Zoom. Let me just wait to see if there is anything on YouTube. So I'll stop the stream and the recording. Nothing. So let me stop the recording. And